Where we left off last week is we were talking about finite probability models. I was thinking I did a problem, right? Did we do the one about like word errors or something like that out of the homework? Okay. So that's one type of probability model, is a finite probability model, and that means you have a finite sample space. All right? So I'm going to do this here. There's two types of probability models. Just to remind you about the one from last week. The first type was a finite probability model. That's the one I worked the problem of. That's the type that you worked for homework, finite. And when somebody's talking to you about a finite probability model, what they mean is you have a finite sample space. Finite sample space means that we can list it. And when I say list it, that means we can write everything down in the sample space and stop. Right? There's like 5 things in the sample space, or 6, or 10, or 100, but you can actually write them all down and stop. Now, I'm going to put something above this. If I happen to use this word, sometimes it pops out of my mouth, discrete probability model. Discrete means the sample space is either finite, or you can write it down. How's that? And when I say write it down, I mean the sample space might be the numbers 1, 2, 3, 4, 5, 6. You keep going. I don't want to get real carried away with the thought about what's going to separate the discrete from finite. A lot of times when we read discrete, and I'm going to use that on you in about 20 minutes here, this idea of something that's being discrete, and that means it's either, in our case, it's finite is what it means. Right? That's another name for finite for us. It has more meaning to it than that, but that's for us. That's the way we think about it. And if you'll remember back last Thursday, and I don't know if you remember back last Thursday, when I first started to tell you about a finite probability model, I wrote up discrete. And I was going to tell you it had a finite sample space. All right? The second type is, the second type of probability model is something called a continuous probability model. What that means is the sample space is an interval of outcomes. You can't write them down. Right? So the finite case is you just write them down and you stop. Or you can write them down, but you can keep writing and you never stop. Here, I can't even attempt to write them down when you're talking about a continuous one. It's an interval, right? It's some interval on the real line of outcomes. All right? Now, I'm going to give you a couple of examples of this. Something that we can think about here. So, my first example of a continuous probability model, what we're looking at here is this interval of outcomes. What I want to do is I want to generate a random number between 0 and 1. So what I mean is I want to choose a random number between 0 and 1. So what I have is I got a random number generator, and it's going to generate me a number between 0 and 1. You can include 0 and you can include 1. All right? When I do this, and I think about generating a random number between 0 and 1, the sample space here is all numbers between 0 and 1. That's the best I can do. I know. Last Thursday, every time I wrote down the sample space, I just wrote it down for you. Why? Because all those were finite. There's no way for me to write down all the numbers between 0 and 1. Can I start? Yeah, I can write the 0 down. What's the next number you write down to pass 0? I don't know. I can't write it down. Right? So I got no shot with a continuous probability model of writing every outcome in your sample space down like I can in the finite case. All right? Now, what we're going to do here is, if I'm going to look at these random numbers, okay, I'm going to let y be the number, the random number between 0 and 1. Okay? So just like in the finite case, where you've got these outcomes, and we assign probabilities, and then we can talk about probabilities of events. And remember, the events are nothing more than outcomes out of your sample space, and we were adding little pieces up. Now, you can't look at me like you don't know what I'm talking about, because if you did the homework, that's what you did in the finite case. The problem you did was like, did you do one about dinner at home or something? The number of nights a week you ate dinner at home, right? And then, I don't know what you wanted to know. There was something about that you ate at home less than 4 nights. So you added up 0, 1, 2, and 3. You had a nice table listing from 0 nights to 7 nights. It was finite, right? And then if you wanted less than 4, you added up the probability of 0 plus probability of 1 plus probability. You added up the pieces. So we were assigning probabilities to particular outcomes in your sample space. It was given to you with the finite case. And then when we had whatever event we were looking at, we just added up the little pieces that made up your event. That's what went on last Thursday, and that's what you did for homework. Well, tonight it's not quite like that. So, for example, an event here would be, let's say I had an event A. Remember, I like to use capital letters at the beginning of the alphabet. An event is supposed to be some collection, some subset of outcomes from your sample space. Suppose I put it like this. So what I'm asking you is, your event A is that you generated a random number between 0.3 and 0.7 when it generated a single random number. That is an event in this case where you're looking at a continuous probability model. Nobody's going to ask you for your event being that you got the number 0.3. They're not going to ask that. They're going to ask you little questions like this. Between 0.3 and 0.7, less than 0.4, greater than 0.6, something like that, where your event's an interval of outcomes too, right? Your outcomes here are between 0.3 and 0.7. Because what we want to know is, how do we attempt to assign probabilities to events that look like that where you're dealing with a continuous probability model? Well, the way we're going to attack this, the way we're going to answer that question is we're going to use areas under density curves. This is going to take us back to chapter 3. That's where we first looked at density curves. Now, I got a question for you about a density curve. I made a big deal about this in chapter 3. When I look at a density curve, and I'm telling you, look, you're looking at a density curve. What's the total area under that curve? It's always 1, right? I must have said that to you 55 times or something, okay? Now, that area back in chapter 3 represented a 1. That area represented a proportion of observations. That area represented a percentage of observations. Well, now that we're talking about probability, that area is going to represent a probability. Now, I'm going to take you all the way back to the beginning of this chapter just for 1 second. Somewhere back there, there's a definition of probability. The probability of some outcome or some event is the proportion of times that that outcome or event shows up if you do it over and over and over again. Correct? Anywhere, and I'm not done with this thought about anywhere that I could calculate a proportion or a percentage, I am looking at the probability, because that's how we have it defined. Remember, it was empirical. Well, we didn't do anything in chapter 3 other than calculate proportions of areas under the density curve or percentages of areas. Well, if I can do that, then I can calculate a probability. My point is this. You know it can't be very long before, if I'm going to talk about density curves, what's my favorite type of density curve? Well, hell, we only know one that we worked with. It was normal, right? Normal curves are going to pop up here again. Z-scores are going to pop up again, because how did I go about finding areas under normal curves? It was to calculate Z-scores and then run the table A and start looking up areas, right? We're back there. The calculations are exactly the same as in chapter 3. The only thing it changes is the language. The calculation's not different. It's how the question's asked, and then in the end, instead of you telling somebody the percentage or proportion, you tell somebody a probability. Same calculation as before. Now, here's what I want to look at. I'm on page 289. I'd like to say a little bit more about this random numbers. And I want to point one thing out to you. Everything I just said to you, right above example 12.9, it says continuous probability model. It says a continuous probability model assigns probabilities as areas under a density curve. That's what we're going to use. The area under the curve and above any range of values is the probability of an outcome in that range. One more time. The area now represents a probability. We find the area like we did before. Now, if I look at this example 12.9 here, all right? It says, the random number generator, and I'm going to add to this, the random number generator, if it is any good, if it's doing what it's supposed to do, randomly generate numbers between 0 and 1, will spread its output uniformly across the interval from 0 to 1, right? It shouldn't favor anything, should it? If it's a good one, it shouldn't, right? It should uniformly be spread across that interval from 0 to 1. It says, as we allow it to generate a long sequence of numbers. Figure 12.4, which is on the next page, please turn over there while I continue to read, is a histogram of 10,000 random digits. In other words, they had a random number generator, and it generated 10,000 numbers, random numbers between 0 and 1. All right? They are quite uniform, but not exactly, so the bar heights would all be exactly 1,000 numbers of each bar if the 10,000 numbers were exactly uniform. In fact, the counts vary from a low of 978 to a high of 1060. Okay. If it was perfect, and we did it 10,000 times, we would expect it to be perfect. When we're generating data like this, you're not going to be perfect, but you can see it looks like it should be uniform, right? All the same value across the interval from 0 to 1. As in chapter 3, we've adjusted the histogram scale so the total area under the bars is exactly 1. We did that before. Now we can add the density curve that describes the distribution of perfectly random numbers. The density curve also appears in figure 12.4. It has a height of 1 over the interval from 0 to 1. It's a square. It's 1 by 1 square, right? So they're telling you that their density curve looks like this. Here's your interval from 0 to 1. And you got a height of 1. That density curve describes this random number, this distribution of this random number generator. It is a uniform distribution. Uniform means it takes the same value across the interval. It all takes the value of 1. What's the area of that square? It's 1 times 1 is the area of the square, right? It has an area of 1. That makes that a density. Oh, I know you're used to seeing these all the time. No, that's a density curve. It's got area 1 under it. Okay? Now it says, it is the continuous probability model for results of generating very many random numbers. Like the probability models for perfectly balanced coins and dice, the density curve is an idealized description of the outcomes of a perfectly uniform random number generator. Okay. There is your density curve that describes this distribution of generating random numbers, these random numbers between 0 and 1. All right? Now, if I've got a question like this, I want to know the probability, and I'm going to write it like this, that you generated a random number between 0.3 and 0.7. That was my question, right? That was the one I had on the previous page. I called that little event between 0.3 and 0.7, I called that A. So what I'm going to do is, just like I always do, there's two values I'm interested in under the density curve. It's 0.3 and 0.7. I'm going to put 0.3 here. I'm going to put 0.7 here. I want to know this area here, because that area represents the proportion of outcomes that are between 0.3 and 0.7. Can anybody tell me what the area of that rectangle is? This rectangle has area. Its height is 1. Its width is 0.4. 0.7 minus 0.3. The area is 0.4. If the area is 0.4, then the proportion of observations between 0.3 and 0.7 is 0.4. The percentage of observations between 0.3 and 0.7 is 40%. The probability when you generate one random number between 0 and 1, that it's between 0.3 and 0.7 is 0.4. Now look, the reason I started with this one instead of starting with a normal curve, the area is the probability. Instead of asking you, okay, we're going to generate random numbers between 0 and 1, it follows a uniform distribution, right? That distribution there, where the height's 1, you get a nice little square, okay? Instead of asking you what percentage of the random numbers that you generate is between 0.3 and 0.7, you would tell me 40%, because the area is 0.4 there, right? Instead of doing that, we're going to generate one random number. One. Not a whole bunch of them, but these random numbers follow that distribution, that density curve. Now, what's the probability that that one you generated is between 0.3 and 0.7? It's still the same area. It's still 0.4. Okay? Look, the reason I wanted to look at that, not so much for this. I wanted you to know what a uniform distribution is, that it takes the same value. It's just a flat. All right? That's all. That's a uniform distribution. Random number generator, if it's any good, it's going to follow this uniform distribution. Now, I don't want to do any more problems here, all right? But here's my thought. That was a uniform density curve. We can use any density curve to assign probabilities. How do I know that? Because the area under the density curve is always 1, and that area represents probability 1. What's the probability of your sample space from the little rules before? That probability is 1, right? When you add up all the probabilities of every outcome in your sample space, you get 1. I can use areas under a density curve to assign, you can use density curves to assign probabilities as the areas under the curve. Now, what's my favorite density curves? We can use normal curves. Remember, what's the two most important things you can tell me about a normal curve? You can tell me about its mean. You tell me about its standard deviation. The mean tells you where it's located. The standard deviation tells you how tall the hump is. Remember, every normal distribution satisfies the 68, 95, 99.7 rule. That's what makes that a normal distribution. Now, here's what I'm going to do. It's something we looked at back in Chapter 3. We talked about heights of women. And it was probably heights of women like age 20 to 29 or something like that. Back there in Chapter 3, we knew that the heights of young women aged 20 to 29 followed a normal distribution. It turns out it was normal with a mean of 64.3. And look, I'm reading here on page 291, the very last paragraph above example 1210. Okay? We knew that the heights of women aged 20 to 29 followed a normal distribution with a mean of 64.3 inches and a standard deviation of 2.7. And that's where you were looking at all of them at one time, right? Somewhere along the line, somebody had a bunch of women, and we measured their heights. They made a histogram, right? Turns out the histogram showed that nice pattern. Somebody drew in the nice normal density curve. We were looking at a large set of data then, all right? Not in this chapter. We're not looking at all of them at one time. What we're going to do is, now I'm going to remind you, chapter 3, heights of women 20 to 29. Follow the normal distribution, and what I got here, the mean is 64.3 and the standard deviation is 2.7. That was chapter 3. Now, what's going to happen here in what chapter is this? Chapter 12. How do I get probability involved in a problem like this? We choose one woman 20 to 29 at random. Here, you're looking at all of them at one time. Here, I'm going to choose a simple random sample of one of them. I've got every name of every woman aged 20 to 29. I labeled them all, and I just choose one of them out. I measure her height, right? So we're going to let her height, we're going to let X be her height. Now, you're going to choose one. You're going to measure her height. You're going to write her height down. You're going to set her aside. You're going to choose another one randomly. You're going to measure her height. You're going to set her aside. You're going to write her height down. If I keep doing this over and over again, do I get all the heights? Yeah. In other words, by doing this, choosing one at random and then repeating and keep going over and over again, you get all I'm going to say is, repeat this choice and measuring her height. At every time, write down her height. You get the same normal distribution. It's the same one. It will be normal, a mean of 64.3 and a standard deviation of 2.7. Are we looking at taking one at a time and then repeating that, or are we just looking at all of them at one time? It's the exact same heights. That's the deal. There's no difference here. It's the exact same normal distribution, whether I'm in chapter 3 or I'm in chapter 12. The only thing that changes here is the language. Instead of looking at all of them at one time and telling me that the percentage that are greater than 72 inches tall, or the proportion that are taller than 72 inches, you're going to choose one at a time, and you're going to ask me, what's the probability that that one you just chose is taller than 72 inches? It's the percentage or proportion from chapter 3 is your answer. It's the same calculation. It's how the problem is stated to you. All right? Now, I'm not going to work example 1210. It's there for you to see. All right? What I'm going to do is this. I'm going to come over here to 1217. I'm on page 293. That's where I want to start here. This is one where I got a continuous probability model. This is the style of question. So when I look at 1217, this is how you attack these. It says, the normal distribution with mean 25.3 and standard deviation 6.5 is a good description of the total score on the MCAT, the Medical College Admissions Test, MCAT test. This is a continuous probability model, so they're telling you that these MCAT scores, total scores, these MCAT scores follow this normal distribution with a mean of 25.3 and a standard deviation of 6.5. All right? It says, this is a continuous probability model because you understand that there's an interval of outcomes here as your sample space. There's an interval of possible total scores on this MCAT test. Now look, everybody look at me just 1 second. I mean, I know your eyes are rolling around in the back of your head. Do you understand why this is not finite? Are you going to write down all the MCAT scores that are possible here? And the answer is no. Does everybody see that they're talking about a normal distribution in the problem? As soon as they start talking to you about a normal distribution, you know you're looking at a continuous probability model. All right? So there's no table to be had like last week or the problems you did for homework. Okay? That's not going to happen. We're going to have to use this normal distribution here to find whatever probability they're asking me for. It says, this is a continuous probability model for the score of a randomly chosen student. You see the word randomly? My questions are going to be about probability. As soon as they tell me to choose one student at random, then the questions are about probability. It says, call the score of a randomly chosen student X for short. So you're going to choose one student at random. And we're going to let X be their score. I have a reason in a moment for using these capital letters at the end of the alphabet. Let me work a couple problems for you. We'll talk about why I keep doing that. Remember, it's X here before I use the Y on you. Yeah. So there's your score. We're going to let that be X. We're going to choose one student at random. And now what we want to know is part A. Write the event that the student chosen has a score of 35 or higher in terms of X. Now, that's nothing new. You did that kind of stuff for homework. What's it mean to be 35 or higher? The score is 35 or higher. That means greater than or equal to 35, right? One more time. Write the event. It's given to me in language. The student chosen has a score of 35 or higher. 35 or higher means that X, the score that on this student's score is greater than or equal to 35. That's what they mean in writing that in terms of X. X is bigger than or equal to 35. Part B says, find the probability of this event. Part B wants to know, what's the probability that the student scored 35 or higher, or if you like, that X is greater than or equal to 35. Now look, I could care less at this point. Notice, I read that big capital P as probability here, right? You chose one at random. It's a probability question. There's my question I want to answer. I have this as my normal distribution, 25.3 and 6.5. The reason I wrote that down there, if I know that I'm looking at that normal distribution, and if I know that's my question, I could care less what the hell else is going on. And I told you the same things back in chapter 3. What's the normal distribution? I need to know the mean and standard deviation. And then what kind of question are you trying to answer here? I'm going to work the problems the same as I did back there. I got a normal distribution. It looks like this. Right? It's got that nice symmetric single-peak bell-shaped curve. It is centered at 25.3. I never did write the standard deviation of 6.5 on there. I don't put that on there. But then I go back to see the question. What do I want? I want X is bigger than or equal to 35, right? So there's one value of the variable I'm interested in, and it's 35. Where in the hell is 35? It's out here, correct? Remember, you're reading, that's the number line there on the bottom. I draw a line. Then I ask you where you want to shade. Do you want to shade to the left? Do you want to shade to the right? Personally, I'd like to shade to the right. Why? It's telling you greater than or equal to 35. It wants you to shade to the right. Now, if I was back in chapter 3, I'd be asking you, are you 1, 2, or 3 away? I don't know, and I don't care. At this point, you've got to calculate a z-score. Remember what it is? Z is equal to X minus mu over sigma. That's how you find out how many standard deviations away from the mean the value you are looking at is. So in this case, Z is equal to 35. That's your X minus 25.3. That's your mean divided by 6.5. Anybody got a calculator? I don't have one today. So if I take 35 minus 25.3, I got 9.7 divided by 6.5. I got an answer of 1.49. Remember, anytime we look at a z-score, I go to two decimal places because that's the way Table A looks, right? That's the way Table A works in the back of the book. So, just to review here for a second. This is telling me that 35 is 1.49 standard deviations greater than the mean. How do I know it's greater? Because it's positive. The z-score positive means you're greater. Z-score negative means you are less than. Okay? Means you're smaller. Now, why do we do all this? Again, I'm still reviewing Chapter 3 with you. As soon as you standardize, it takes you to the standard normal distribution. Remember, that's the one with a mean of 0 and a standard deviation of 1. Your little z-score is here of 1.49, and then we still shading to the right. Whatever way you shaded in the first picture, you're going to shade that direction. Now you go to Table A. And in Table A, what you're going to do is you're going to go to the row that is 1.4, and the column is 0.09. When you do that, you're going to find the row that's 1.4. You're going to find the column that's 0.09 because that's making your z-score of 1.49. You're going to read across. You're going to read down. You're going to come to a number that's point something, something, something. What do we get off of one? What do we get? Tyler, did you get that? You check me. 1.4, 0.09. What do I get here when I do this part? What do I find when I look up? What you got? 9319. One more warning. The table always tells you the area to the left of the z-score you're looking at. So it's telling me that this area here is 0.9319. If I want the area to the right, and I know the total area under the curve is 1, I'm going to take 1 minus 0.9319. That's going to give me 1860. 0.0681. Okay, if I was in Chapter 3, I would be telling you that the proportion of MCAT scores that are greater than or equal to 35 is 0.0681. Or I would be telling you that the percentage of MCAT scores that are 35 or higher is 6.8%. But I'm not in Chapter 3. I'm in Chapter 12 here, and what happened was you chose one student at random. And now what you want to know is what is the probability that they scored 35 or higher? So going back up here, your probability that you're looking for is the probability is 0.0681 that this randomly chosen student scored 35 or higher on the MCAT test. Now look, I'm going to circle something here. That's different from before. All right, oh, you choose one at random. Everything from where I started Part B to the bottom is the exact same as I had done before. And then when I come back and answer my question, well, as soon as somebody tells me choose one student at random, let X be their score, their MCAT score. Now, what's the probability that they scored 35 or higher? My answer is going to be in terms of a probability. But a probability is a proportion. The proportion is 0.0681. The probability is 0.0681. So that little p stands for proportion, percentage, probability. I didn't do anything different. I'm not so sure I didn't do this problem back in Chapter 3. somewhere. All this stuff from right there down, that got nothing to do with probability. That is finding the area under a normal curve. Where's the probability come in? Well, it's all at the top here. Oh, no, you chose one at random. The probability you chose when you chose one at random, they scored 35 or higher is 0.0681. It's still that area, it's still that proportion. Same problem. Okay? Now, look, I can't walk away just doing one of them. Okay? So, these are kind of hard to come by here in your... they're more about finite probability models in this chapter than they are continuous probability models. So, if we come over here to page 294, and I look at 1219, okay? Let's do another one. Because, look, I'm doing two things for you. I'm reviewing chapter 3 in case you don't know. Because we got to review that a little bit. It's been a while since we did z-scores and table A and all that. And then, okay, so here's the language. It's still the same calculation. So if I look at 1219, all right? Here's another one that's going to be a continuous probability model. It says, a study of 12,000 able-bodied male students at the University of Illinois found that their times for the mile run were approximately normal, with a mean of 7.11 minutes and a standard deviation of 0.74. So they're telling me that these, what is it, run time? The run time for the mile, I'm just trying to keep track of you what variable we're looking at here, is normal with a mean of 711 and a standard deviation of 0.74. Right? So they follow a normal distribution. It says, choose a student at random and call his time for the mile Y. Choose a student at random let Y be their time. I'm going to circle that up front this time. Now, you do realize whatever kind of questions they're going to ask me here in Part A and Part B, these are going to be probability questions. And you're asking me, how do I know that? Because you just chose a student at random and you let Y be their time for the mile. Start with choose a student at random. The question is going to be about probability. So, Part A says, say in words what the meaning of the I'm going to say it to you in words here because I'm reading it, right? The probability that the run time was greater than or equal to 8 minutes, right? So I'm going to write these out for you. Part A says, translate those symbols into language. You want the probability that the student runs the mile in 8 minutes or longer. Now, look, as long as you're telling me that whatever we're looking at here, they're running the mile in 8 minutes or more, at least 8 minutes, there's more than one way to write the English for these symbols. The rest of Part A says, what is this probability? So we need to find what's the probability that the run time for this one randomly chosen student is 8 minutes or more, greater than or equal to 8. You have a normal distribution with a mean of 7.11 and a standard deviation of 0.74. So we draw that normal distribution. We know what it looks like. The mean is right here at 7.11. 8 must be there. We draw our line. Which way do you want to shade? Well, personally, I want to shade to the right because it tells you to shade to the right. The next step is always at this point is to calculate your z-score, which means to standardize that 8 that showed up in the question. You're going to take 8 minus 7.11 divide by 0.74. Tyler, did you get me? You got me a z-score? 1 point. .203, so I'm going to give you just 1.20. We go to 2 decimal places, right? That means 8 is 1.2 standard deviations to the right or greater than the mean. That takes you to the standard normal distribution, this one right here. Again, just like before, if you don't want to draw all the pictures, nobody's going to get excited. I draw the pictures so that I can keep track of what's going on here. You wanted the area to the right before, you want the area to the right now. You go to table A. You're going to go to the row that is 1.2. The column is 0.00. You're going to get a number here of point, what? 8849. The table always tells you the area to the left is 0.8849. I want to the right. So the area to the right here is 0.1151. Now, depending on what chapter I'm in, what I know is 11.5% of all these run times are 35 or higher. Is that not right? 0.1151?
Yeah, I did it backwards.
Okay. Okay. If that's the area to the right of 35, then the probability that the student you chose at random that ran the mile in 8 minutes or longer, that's your number. It's 0.1115. Excuse me, 1151. Okay? Now, there's a part B here. Part B says, write the event. The student could run a mile in less than 6 minutes in terms of values of the random variable. In other words, take the English language and convert that to symbols. So, part B says, one more time, write the event that the student could run a mile in less than 6 minutes in terms of y. Well, y is the run time, right? Y is less than 6 minutes, right? That's my symbols. And then obviously the next part says, what is the probability of this event? What you're trying to find is the probability that the run time for the mile is less than 6 minutes. You have the same normal distribution. Mean 7.11, standard deviation is 0.74. I'll draw you the picture. Here's the picture of what we're looking at. Here's that normal distribution. There sits your mean. 6 is over here this time. Remember, we're reading from smallest to largest. We draw our line. Why do I want to go to the left? I'm less than 6 minutes. You got to standardize. You got to calculate a z-score. You take the value of the variable you're trying to standardize. You subtract off the mean, and you divide by the standard deviation. That's going to give me a z-score of negative 1.50. That means that 6 is 1.5 standard deviations smaller, 1.5 standard deviations to the left of your mean. That takes you to the standard normal. You always know when I'm giving you the standard normal because I come right as normal, mean 0, standard deviations 1. Mean 0. Here sits my z-score of negative 1.50. I still want to the left. And every time that I get to this point, you know I'm running for table A. This time when I go to table A, my row is going to be the minus 1.5 row. The column is going to be 0.00. You're going to find minus 1.5 row, 0.00 column, read across, read down. You get a number of point something, something, something. 668. The table always tells you the area to the left of the z-score you looked up. So what you looked up is exactly what you need this time, 0.0668. It means the proportion of run times that are less than 6 is 0.0668. That means the percentage of run times that are less than 6 is 6.7%. It means if you chose one student at random and you're interested in the probability that the runtime is less than 6 minutes is 0.0668. That is your answer here. 0.0668. Now look, I did 1217, I did 1219. I was interested in two things there is, can we translate the symbols to language? Can we translate the language to symbols? Because obviously we need things in terms of, we got to know what we're looking at here. You know, what's it mean 8 or higher? What's it mean less than 6? What are you looking at here? These calculations, this calculation in B, from there down, I have no idea whether I chose one at random or whether I'm looking at all of them and I want a percentage proportion or whether I want a probability. I have no idea. The language in this chapter changes nothing from here down. Those are the problems I worked back in chapter 3. Same thing here. In part A, from there down, I got no idea whether you chose one at random, you want to know the probability, or you want the percentage proportion. That's all exactly the same. And the same thing with 1217. Other than you chose one student or chose one whatever at random and the question is going to be about probability, the calculation is the same. The only thing that changed here is the language. Okay? That's the deal with all this. Now, the only other thing I have left here is I got a couple definitions for you. All right? Out of this chapter 12. And we've got this idea of something called random variables. And I'm going to give you random variable, and I'm going to turn these into definitions. And then the other one is probability distribution. Now, where I'm at is I'm in your book, and I'm on page 293. There's a little box there. It says random variable. A random variable is a variable whose value is the numerical outcome of a random phenomenon. Translation. A random variable is a number, right? Its value is a number. That number is coming through some random phenomenon, like rolling a die and recording the up face. Having a students run the mile and recording their time, measuring the heights of women aged 20 to 29. The catch is a random variable has to be a number. Like tossing a coin and recording heads or tails, that's not a random variable. A random variable needs to be a number, a numerical value from a random phenomenon, something that's exhibiting this chance, this random behavior. Okay? So all I'm telling you is you have a new type of variable. Hell, what's a variable before? It's any characteristic we measure on a set of individuals, right? Back to chapter 1. Well, now it's a random variable. Well, random variable means you got to have a number. It's a number that comes from a random phenomenon. That's what you're measuring about the random phenomenon. Whatever these numbers are, what are the outcomes is what you're looking at. And then there's the second one here. The probability distribution of a random variable. Now look, people don't give you that. People talk about a probability distribution. You have to know it's of a random variable. And it says, the probability distribution of a random variable x tells us what values x can take and how to assign probabilities to those values. So a probability distribution always tells you two things. What values X can take. You know what a probability distribution of a random variable tells you? What are we talking about here when it tells us what values X can take? I'll just put it like this. What values X can take. It's telling you the sample space, folks. That's what the values are. The values that X can take, that's your sample space. And two, how to assign probabilities to those values. So probability distribution of a random variable always tells you two things. What values your random variable X can take. It tells you the sample space. And then it tells you how to assign probabilities to those outcomes, to those values that are in your sample space. That's what a probability distribution does. Now, I'm not going to shut up yet. In Chapter 1, we had a variable. That was any characteristic we measured, right, on a set of individuals. You had a distribution of a variable back in Chapter 1. The distribution always told you two things. It told you what values your variable could take, and it told you how often it took them. Yes? That's all the way back to Chapter 1. Well, now we're in probability. And everybody loves to talk about, oh, well, let's look at that random variable. Right? Let's look at the values, these numbers that come from this random phenomenon. Let's look at what values it can take, right? So you talk about a random variable. So you added the word random to variable, and then you add the word probability to distribution. Because anytime you're looking at a random variable, you describe that random variable, right? What values it can take and how often it takes them by talking about its probability distribution. Because you see this part right here? That's the sample space. That's what values your random variable takes. That's the same as number 1 back in Chapter 1. You see this part right here? If I can assign probabilities to those values, am I telling you how often they occur? Doesn't probability tell you how likely something is to happen? Probability tells you how often something happens. The higher the probability, the more often it happens. Now, I understand it's not telling you it's going to happen 5 times, but it's telling you the same thing. We stick these together. Random probability. The hell, that's just a variable in a distribution. But it's telling you the exact same thing. Okay? Now, one other thing. In this class, we denote random variables by a capital X, capital Y. I guess if I had to go that far, I'd give you a capital Z. When we speak of random variables in this class, we like capital letters at the end of the alphabet. X, Y, Z. Okay? Now, the other biggie here is the random variable that we're mainly interested in this class being a stats class. These other things are giving us something to work with to talk about probability. X bar, does anybody remember that notation? That's all the way back to Chapter 2. That's the mean of a set of data, right? That's a mean of a sample here, right? X bar is a random variable. So in other words, X bar exhibits random behavior. X bar must take values from some random phenomenon, right? But it must be described, that X bar must be described by some probability distribution. The reason I wrote it right here is we're not going to change the notation, right? If we're talking about probability and everything and you see X bar, oh, it's a random variable, right? So my question is how does this X bar become a random variable? What's the random phenomenon here? Let's think about it like this. Suppose we choose a random sample, right? I don't care. We chose a random sample of students. 100 of them. And I'm going to measure their heights. And I'm going to take the average height. Can anybody tell me what the average height is of those 100 random students? And the answer is no, it's unpredictable, correct? When you go and you take a random sample of whatever, and you measure whatever quantitative variable you're interested in, and you calculate x bar based off of that quantitative variable, there is no way you can tell me what that value of x bar is going to be until we do it. It's unpredictable at any stage, right? That's what that chance random behavior is. It's unpredictable at any time you take a sample, it's unpredictable, right? You can't tell me what the value is. But if it's actually a random phenomenon, this idea of choosing a random sample and calculating x bar, it must settle down to a regular pattern. Yeah? So you got to give me a little break here. If I'm telling you this, there's no doubt that we can take a random sample of 100 students, measure their heights. There's no way you're going to tell me what the average height is until we do it. I have no problem. That's like flipping a coin. Can you tell me whether heads or tails shows up? No. Right? I have no problem convincing you that. It's the last part. If we do this over and over again with x bar, take a sample, calculate x bar, take a sample, calculate x bar, what pattern does it settle down to? It has to settle down to a pattern. When you flip a coin, did it settle down to a pattern? Yeah, about half the times head shows up and about half the times tail shows up. Well, this one here is so important to us. What chapter is this? 12? 13? They dedicate a whole chapter about, okay, what the hell's a regular pattern? And it's actually chapter 15 here. We're going to come back and we're going to talk more about x bar as a random variable, and we're going to see that in chapter 15. If I got all my chapters correct here. Yeah, it's chapter 15. Okay? We spend a whole chapter about, okay, so what the hell does this look like if you do this over and over again? What's the regular pattern you settle down to? If I'm going to tell you it's a random variable, it has to. Remember, it's a numerical value coming from a random phenomenon. What pattern does it settle down to? It has to settle down to a pattern. That's chapter 15. Now, the very last thing I have here. Just like there are two types of probability models, there are two types of random variables. One, I don't use finite here. I'm actually going to use discrete. And continuous. Okay, how do I know it's discrete? In our case, you have a finite sample space. In other words, your random variable can only take on a finite number of values. You can write them down. There's a finite sample space there. What about a continuous random variable? An interval of outcomes. Right, so that's corresponding to the probability models being a finite sample space or an interval of outcomes. You have a discrete random variable or you have a continuous random variable. So then we come over here. I'm not interested in personal probability. Let me ask you this. That one we did in 1217 about the MCAT scores, right? We did that problem. Remember they followed a normal distribution, mean 25.3, standard deviation sigma equal to 0.5. We said choose a student at random, let x be their score. That x is a random variable here, right? Because that's coming from a random phenomenon because you chose one student at random. Yeah? Is x a continuous random variable or a discrete random variable? Wasn't everything described by a continuous probability model? That's a continuous random variable. You come over here to 1219, where we did the one about running the mile. That was described by a normal distribution with a mean of 7.11 and a standard deviation of 0.74. We chose a student at random. We let y be their run time. Is that y a continuous random variable or a discrete random variable? That is a continuous random variable. There was an interval of outcomes possible here for the runtime. You come to your homework problems. 1245 that we did last week, the one about spelling errors, right? I'm on page 300 here. Spell checking software catches non-word errors that result in a string of letters that is not a word, as when when THE is typed as TEH. When undergraduates are asked to type a 250-word essay without spell checking, the number X of non-word errors has the following distribution. The value of X was either 0, 1, 2, 3, or 4, and then they gave you the probability of each one of them. Part A, I just left it alone, says, is the random variable X discrete or continuous here? Why? What's your sample space? The sample space is the number 0, 1, 2, 3, or 4, right? That is finite. This is a discrete random variable because you have a finite sample space. I'll be honest with you. Everything we did up till tonight, if you were getting a numerical outcome like rolling a die and adding the up faces, that's a discrete random variable. Rolling a single die and recording the up face, that's a discrete random variable. I'm trying to think what else we did. Flipping the coin, that's not a random variable, right? It has to be a number. Okay? That's the end of chapter 12. That takes care of everything. Now look, I understand there's a lot going on there for you. I got that. There's some definitions you got to know. There's some little rules you got to know. You got to know the difference between discrete being finite, continuous being intervals. And I can make it real simple for you. When somebody's talking to me and I'm looking at something, just like I can look through the problems real quick to tell you whether it's discrete or whatever, if it's discrete, I'm going to see a table. It's going to list the sample space and it's going to give you the probabilities. That means you've got a finite sample space. As soon as I read something, they're telling me that this variable that you are looking at, this random variable follows this normal distribution, I know you're looking at continuous, right? Because there's an interval of outcomes there. And then I'm working the problems like I did tonight. You cannot, I repeat, we can't miss any of the questions where it's discrete. And somebody gives you a table, here's your outcomes, here's the probabilities. You can't miss those questions. You're just picking out the pieces and adding them up. Shit, it don't get no easier than that. Right? That's what you did for homework. Okay, what the hell does it mean? You want X to be, I don't know, if it was greater than, less than 4. Well, you add 0, 1, 2, and 3, whatever those. It don't get no easier than that. I'll give you tonight, I'm back to chapter 3. I'm looking at normal distributions again. Well, depending on how you did with chapter 3 and the normal distributions, that's going to tell me how you do with these continuous random variables, these continuous probability models. Because it's the same calculation. All right? Now, here's the thing about chapter 13. I know where we're at. I know the language we need. I know the things we need to look at here. All right? So, the thing about chapter 13, I will give you that the title of it is General Rules of Probability. Well, I can make you all go home and never come back in this chapter, and I don't want to do that to you. No, because when we look, I've done pretty much everything in chapter 12 with just saying, okay, if it's discrete, everything's listed for you. If it's continuous, right, we're going to have a normal distribution. We're going to go through there. And there was a couple, definitions back there. That's what really went on here, right? And so I haven't shown you any other formulas. But in chapter 13, we can write formulas all over the place here. I'm only going to write the ones I need. In other words, I can turn this into a real-looking probability class, or we can just do what we need to do with all the language that I can put with it and showing you just the little things that we need, right? So I'm not going to get nuts where everything's got a formula here. I don't care. My first thought is this. I want to turn to page 304. there's 4 probability rules. They are reminding you the 4 from the previous chapter, right? Every probability is a number between 0 and 1. The probability of the sample space is 1. Disjoint, and you want or. You added them. You've seen those 4 already. Those were the 4 I wrote down last Thursday, probably really close to the beginning of class. Those were the 4 rules we had. Now, the way I'm going to attack the rest of this is, in this chapter, there's 3 things I want to talk about. 2 of them are tools for helping me keep track of probability, helping me find probabilities by drawing myself a picture. That's 2 out of the 3. And the third thing we want to do here is, does everybody remember two-way tables? Chapter 6? That's where you had 2 categorical variables and you classified everybody, and we had this table, we had the row variable, we got the column variable. Does anybody remember in chapter 6, did we calculate all kinds of percentages off a two-way table? We had marginal distributions, you had conditional distributions, you calculated percentages, yes? Does anybody hear me a half hour ago? Anywhere that you can calculate a percentage from before, I can turn it into a probability question now. So two-way tables are going to be used to calculate probability, right? Calculation's the same. It's the wording at the beginning of the question, all right? So my first thing is this. The first thing I want to look at is Venn diagrams. It's a picture. It's a picture to help me keep track of things, all right? So what a Venn diagram does, it's going to show the relationship between 2 or more events. Now, when I say 2 or more, and we're going to draw a picture, for us in this class, it's always 2. If we was going to take a little more probability, we'd show you 3, and I don't even want to think about showing you the relationship between 4. So for us, it's always 2. Now, the Venn diagram works like this. It always starts with a rectangle. What the rectangle represents for us in the Venn diagram, this represents your, anybody know what that capital S is? That's your sample space, right? That's all the possible outcomes of your random phenomenon. They all have to fit somewhere inside of this rectangle. Now, the first one I'm going to draw, you remember when things were disjoint? Remember? I talked to you about disjoint when we wanted to talk about the probability of A or B. If they're disjoint, you added. I can draw you a picture here with a Venn diagram of what it means for those 2 events to be disjoint. Remember, they had no outcomes in common. Here sits your A. Here sits your B. That is a picture of disjoint. There's no overlap, right? There's no outcome that can be in A and be in B at the same time. That is a picture of disjoint. No outcomes in common. Okay? See, because what happens is, what you're going to see me do when I work a problem, I'm going to put the outcomes where they belong. If the outcome belongs in A, I'll put them in A. If they belong in B, I'll put them there. If they belong somewhere else in the sample space, I'll put them outside. Now, I just wanted to show you the picture of disjoint, because normally when I draw you a picture of 2 events, whether they are disjoint or not, this is the way I'm going to draw it for you. That represents your sample space. Here sits my A. Here sits my B. This would be not disjoint. I have outcomes in common here. Right? Now, right here. Those are the outcomes in common. Those are the outcomes that are in A and they're in B. And I'm actually going to write that. That's the ones that's A and B. That's usually our standard picture. There's usually, the reason we're looking at the Venn diagram is there's usually things that are in common. Now, before I do any problems or anything like that, I want to take one of these and I want to go back to something we did before. All right? And what I want to do is I'm going to give you an example. And my example is I want to deal a card. Okay? The two events that I'm interested in is A, that you get a king, and B is you get a red card. Okay? So a Venn diagram would help me keep track of what they have in common, how many cards are wherever, right? So what I want to do is this. Here's my Venn diagram. Here sits my A. Here sits my B. And that's my sample space. Now, anytime I start filling in where the outcomes in your sample space go, I always start on the overlap part. Now, I'm not going to tell you what cards they are. What I want to know is how many cards there are. How many cards go in the overlap? How many cards are king and they are red? Remember, that's the and, right? That's the overlap there. The ones that are in common are the ones that are A and B, red and a king. How many cards are there? Everybody understand there's two red kings there, right? That's the king of hearts and that's the king of diamonds. Now, does everybody see this part right here? That's the rest of the red cards, correct? The two red kings are already in there. How many red cards? Excuse me, A. That's the rest of the kings, right? There are 4 kings total. The 2 red kings are there. How many cards go in that little spot there? My man says 2. Thank you. That's the king of spades, and that's the king of clubs, right? Does everybody see this part over here? That's the rest of the red cards, right? The 2 red kings are there. How many red cards are left over? Does everybody understand where I got my numbers from? In the middle there, in the overlap, the cards that are in common are the 2 red kings. Out here where I got the little red arrow, that's the other kings. That's the 2 black kings. Out there where I got the blue arrow, that's the rest of the red cards. There's 24 cards there. Now, before we go any further, because I don't have all the cards on there, right? Remember, when you deal a card, there are 52 possible cards that can show up there, yeah? So, you see that there are 26 red cards. There's 2 plus 24, the 2 in the overlap plus the 24 other ones. You see there's the 4 kings there in the A, the 2 in the overlap and the 2 that are outside of there. How many cards are left? How many cards go on the outside? How many cards are not red and they are not a king? Does everybody understand that there's still 24 cards here? That's the rest of the black cards that are not kings. Now, if I go here and I add all those numbers together, what should they add to? Every card should show up one time, right? You didn't want to count anything twice. 24 and 24 is 48, plus 2 is 50, plus 2 is 52. All the cards are there. Okay? Now, do you remember when I wanted to know the probability of A or B? The first thing you're supposed to ask yourself is, are they disjoint or not? If they're disjoint, you just add the probability of A plus the probability of B. If they are not disjoint and we did this problem, we got to pay attention. You don't want to count anything twice. You know what the Venn diagram does for you? It stops you from counting things twice. How many cards are a king or red? There's 2 plus 2 plus 24 divided by 52. What did I add? Those two plus that one. Those are the ones that are red, or they are kings. And the Venn diagram stopped me from counting those two red kings twice. So whatever this turns out to be, this is 28 out of 52 here, which is 7 out of 13. That's what a Venn diagram does for me. Now, if you want to see what I just did to you, there's some kind of probability rule here somewhere. You're not going to see me write any rule down. I just kept track of what was going on here, and we made sense of it. We didn't count anything twice, right? We counted up the right things by just counting each piece by themselves. Okay. The last thing I want to talk about here, right? So the reason that I came back to this is because when I see a Venn diagram, all of a sudden I start thinking about disjoint or not. I want the probability of A or B. This was a nice example for our first one, for me to draw a Venn diagram of where all the little pieces fell. And what I mean by pieces are where all the little outcomes fell. I'm not done using the Venn diagram. We're going to do it again on Thursday. But the other thing I'd like to talk about is two events being independent. A and B are independent events. Look, you already know what the hell an event is. This is your word. Independent. What's it mean for them to be independent? We know what it means for them to be disjoint. They have no outcomes in common. Independent means if knowing that A occurs, in other words, you know the event A occurs, does not change the probability that B occurs. Now, I'm giving you the definition of independent in language. You got two events, A and B. They are independent if you know that A has occurred, does not change the probability that B occurs. The simplest thing I can give you about independent events is let's flip a coin twice. A is the first flip is a heads. B is the second flip is a heads. Let's say we know the first flip is a heads. What's the probability the second heads is? It's still 50-50. Did knowing that the first one was a heads, did that change the probability of the second one? Those are independent. If you wanted the simplest thing I can give you that are not independent, let me deal you two cards from a deck. The first card is a red card shows up. The first event is A is the first card's a red card. B is the second card is a red card. Let's say we know the first card's a red card. It's laying on the table. Does that change the probability that the second card's a red one? The probability the first card is a red one is 26 out of 52. There's a red card laying on the table. Does that change the probability the second card's a red one? That's 25 out of 51. Those are not independent. That's exactly what we know here, right? If you know that A has occurred, that does not change the probability of B occurring, of the next thing happening. The only other thing I can write here is, if you know they are independent, then the probability of A and B, you just multiply them. So if you're going to flip a coin twice and you want to know the probability of getting heads and heads, they're independent, right? It's a half times a half. I'm giving them to you in that form for a reason, because when I think about independence, I think about doing one thing and then another, like a sequence, right, of things. And if they're independent, then whatever the sequence is I'm looking at, I just multiply the probabilities together. That's the reason. That's how I think about independent. Now, I'm going to give you a little twist on Thursday. You got two definitions. Disjoint means no outcomes in common, no overlap, right? Nothing in the center there, nothing in the A and B. Independent means if you know that A has occurred, that doesn't change the probability of B occurring. If that's the case, and you want the probability of A and B occurring, multiply them. Go back and look in your notes. If you write everything I write, when I wrote probability of A or B, I underlined the or when we talked about that. Or you're worried about disjoint, and you're worried about independence. Right? That's the only time that's true, when they're independent. Disjoint, the only time you add each one of them is when they are, the or is disjoint. Look, go ahead. You guys walk to the door. I'm going to keep talking. Even when I read the problems, my voice changes. The probability of A or, I make a point with the or, right? Same thing here. Probability of A, I can't help it. That's what's going on in my head, because when I see or, what the hell is the important word? It's the or, right? With and, that's the important word. That's telling me what I'm looking at. Everybody be careful going to the house. We'll pick up here on Thursday. Thanks for standing and not walking out. Appreciate it.